Hi, welcome everyone to session 12. In this session, I will discuss about classification. What is a classification problem and how classification problems are different than regression problems? What are some of the examples of classification problems? And then we will take a data set and build our first classification model. As you have already seen, all machine learning problems can be categorized into two different problem types: supervised problems and unsupervised problems. And as of now, we are going through supervised kind of problems. And there are two types of supervised problems: classification and regression. So we have already explored regression in the previous session, which is predicting an outcome or a label which are continuous or numerical in nature. For example, we have explored in detail how to predict the resale value of an used car. So now we will get into classification problem type from this session onwards, and we'll look at how to predict an outcome or level which are categorical in nature. For example, customer churn. Some of the examples of classification problems, like classifying or categorizing an email or emails as spam, or not spam, based on their the email content, the subject line, or any other feature of the email, or identifying a credit card transaction as either fraudulent or legitimate transaction based on the patterns and anomalies, or predicting if an employee will leave or not leave an organization in the next 6 months, predicting whether a loan applicant is likely to default or repay, a very popular application of classification problem. And we predict that based on loan, their financial history, credit score, and other factors. Another classic example is classify if a social media post customer reviews are positive or negative or neutral sentiment to understand the public opinion, or predict whether a customer is likely to churn or stay with a service provider based on their historical usage, behavior, and demographic data. So these are some of the classic examples of classification problem types. And all these problem types, all the classification problem types are basically categorized into two types. One is binary classification or multi-class classification. There are some advanced types also there. We'll come back to that a little later. But as of now, let's look at, there are two kind of problems in classification. One is binary classification. For example, if an email is a spam or not a spam, or the transaction is a fraud or not a fraud. So we are classifying between two classes, this binary classification, but there are also problems which are multi-class. For example, if a particular customer review, is it a positive or a negative or a neutral? So we will classify among three different classes. So that these are multi-class classification problems. So what we'll do is we will we'll take a data set and experiment through that. So for this I have already created a directory in the GitHub repository called session 12, and uploaded a notebook called classification HR attrition analysis, and a data set, corresponding data set. So let's first explore that, the problem type. So if you can download and upload them into your Jupyter notebook and open the notebook called classification underscore HR underscore attrition underscore analysis. So here the problem type is HR attrition analytics. So if you look at the description, basically says that human resources are critical resources for any organization, and organizations spend huge amount of time and money to hire and nurture their employees. It's a huge loss for companies if the employees leave, especially the key resources. They could be a project impact cost to the company, or they can also be the hiring of new employees to replace those who have left, uh, cost to the company as well. So if HR can predict whether employee are at risk of leaving a company, it will allow them to identify the attrition risks and help understand and provide necessary support to retain those employees, and do preventive hiring to minimize the impact to the organization. So one is, um, the classification problems can help you to understand what could be the key factors impacting employees' decision to stay or leave the organization, and based on that, they can create policies or strategies to retain good employees. They can create strategy. So the models can actually help us understand what are the important factors. Second is, they can also identify at every employee level what is the risk, of that particular employee staying, leaving an organization. So and then they can take necessary action, or intervention, right, at employee level, specific employee level, to basically retain those employees, especially if those employees are critical to the organization. So here we'll take a data set which is in the Kaggle, it's given, and it has the variables. There's a variable in that, it's called left or not left. So this is the outcome variable. If the value is 0, if the employee did not leave the organization. So 1, if the employee has left the organization. So to accomplish this kind of task, you have to historically look at data sets, samples of those employees who has left the organization and who have not left the organization, and employee who have left the organization just prior to them leaving, what are the attributes of those employees, right? Some of the attributes we'll discuss now. And people who have not left, what are the attributes as of now for those employees, and then we can look at those. For example, here some of the variables that might impact, we don't know yet. These are possible factors. Only when after building a model we'll get to know which are important and not. And some of the factors that have been captured are satisfaction level, which means which captures how much the employee is satisfied. This kind of information typically is captured in an organization through, like, uh, employees voice of workforce or survey periodically, and there's an index that gets created based on the response the employees give on that survey. In this case, it is an index or value is created between 0 and 1, and 1 means most satisfied and 0 means least satisfied. Last evaluation, which is employees evaluation. This is like performance appraisal, how that employee is evaluated by the organization. This is again captured in a value between 0 to 1. 1 means an excellent, appraised, and 0 means bad. Number of projects the employee has worked on so far. So how many projects the employee has also worked on, that could be a factor. And average monthly hours, which actually captures how much the employee spends at work every month. This could also be an indicator of work-life balance. And the interest of the employee uh, in the project assigned to the employee. Time spent in the company, which is for how many years the employee is there in the company, 1 year or 2 year or 3 year or several years. Work accident, if the employee has met an accident, so this data might be coming from an domain or industry where probably manufacturing. So there's a possibility that employee might have face a work-related accident. And does that actually affect employee's decision to stay or leave in the organization? Whether the employee has gotten promotion in the last 5 years, 0 if did not have any promotion last 5 years, and 1 if had promotion, and which department the employee is working for, right? So there could be different patterns based on different departments. And there is of course one more variable not mentioned here, is salary. Whether it's captured as a high, medium, and low. So if the employee is in a high salary bracket or a medium salary bracket or low salary bracket, and we'll see how these factors are helping us to predict if an employee is going to stay or leave the company. So let's first load the data set. We'll import necessary libraries like pandas, numpy, and matplotlib and cbun for exploration. And the data is actually given in the hr,scp.csv file. It's a comma separated file, and we'll capture the data into hrdf, hr underscore df. Let's quickly look at some of the samples randomly. And if you see, this is an employee, and you can think like this is the employee ID or index number, and this employee, the satisfaction is not so good, not so bad, so 0.49. Evaluated pretty okay, 0.79. Number of projects the employees worked on so far is 5 projects. Spends about 177 hours at work. They're in the company for the last 2 years, did not meet any accident, and did not leave the organization. Did not get any promotion in the last 5 years. Works in the department of support, and is actually in the low salary bracket. And you can see there are employees which did not leave the organization, and there is of course a sample here which the employee has left the organization. And let's look at how many samples we have, data points. We have about 14,999. It's quite a large sample we have, and about 10 columns, the ones that we had discussed already. And we can see there are no null values here. This is a pretty clean data set, so there are no missing values here. We don't have to do any missing value imputations in this data set. And which takes about 1 MB in memory. So before we can proceed and do the modeling, the classification model, let's look at some exploratory data analysis and understand how some of these factors might influence the outcome or employee's decision to leave or not leave an organization. Let's say we'll ask a question: how satisfaction level influences employees' decision to leave an organization. So I think satisfaction level looks like a very important factor, and by intuition you can say that people or employees which are very low satisfied typically tend to leave, and high satisfied probably not leave an organization. That's what the intuition says. But let's go and look at how what the data is saying. So in this case, we'll do a histogram because satisfaction level is a numerical feature. So let's look at a histogram, and we will plot satisfaction level on the x, and we want to separate both the categories now. So this is a very important factor, especially when you are exploring data sets which are primarily meant for classification kind of problems. So if you want to compare two different categories, so you can bring in a hue factor. So in this case, what we'll do is you look at the hue variable left, and you look at what are the unique values for that. So here the unique values are 0 and 1, right? So it will create a histogram for 0. It'll separate the data for the left value equal to 0, and you create a histogram, and it'll create another histogram for the left value of 1, and then overlap on each other for comparison. And I'm going to create a histogram with a bins which is ranging from 0 to 1 because the satisfaction level varies from 0 to 1 with a bin width of 0.1. So we can look at 0.0 to 0.1, 0.1 to 0.2, and within each bin we will see what is the proportionate of people staying and leaving, right? And we'll stack it. So let's see that. And you can see this is a histogram, and the blue ones are given as a not left, and the yellow one is given as a left. And you can see that between 0 to 0.1, 0.2, and so on and so forth. Initially, I think except this particular range, there may not be many people here. Most likely people are leaving, right? People who are satisfaction level is less than 0.5. There are more people leaving than staying. So if you look at the height of the yellow boxes are much higher compared to the blue ones. But beyond 0.5, you can see the mostly people are staying. But there is a bump here. You can see that there is also an increasing people who are very highly satisfied, which is basically from 0.7 to 0.8 and 0.8 to 0.9. People are extremely satisfied, and yet they are leaving. So this could be because of some other reason that employee are very satisfied, yet they are leaving. So we look at some other factors as well. So this is an interesting plot, especially when you're trying to compare two different categories. So here, this plot, especially very useful when you're comparing two different features. One of them is numerical, and the other one is categorical. So if you see, we're comparing the satisfaction level and left. Satisfaction level is numerical and left is categorical. So you can do an overlap plot like this histogram, and we can give the categorical variable as a hue and the x value for which we want to look at the frequencies as the numerical feature. So this can be done for other features as well. For example, last evaluation or average monthly hours and number of projects and so on and so forth. Now let's look at another question: how time spent in the company influences employees' decision to leave. For example, as an employee becomes older and older in organization, let's say after joining, it's 1 year, 2 year, 3 year, and 4 years, and what is the pattern of people leaving? So, do they tend to stay in the company as they um, get more and more experience, or people tend to leave? So for this again we can look at a plot called count plot, because time spent in the company is a discrete variable. It's not a continuous value. Time spent in the company is like 2 years, 3 years, 4 years, and so on and so forth. And we will look at with respect to the left. So the count plot we will do for time spent in the company as the x value. Again, we will look at the left value 0 and 1. So people who have left, what's a pattern, and people who have not left, what's a pattern. And if you draw this plot, this is a count plot, and x value is the time spent in the company, and this is the count, and each of the discrete values in the time spent in the company, like the employee with 2 years in the company, 3 years in the company, 4 years in the company, and so on and so forth, and further subgrouped into people who have not left and left. Again, the blue one is left here, and the yellow one is not left. And if you see, when people have only 2 years experience in the company, 2 years old, there are more people staying than leaving. But when it becomes 3 years old, you can see the proportionate of people leaving a little higher compared to the 2 years in the company. And that still increases when it becomes 4 years. So when people stay for 4 years in the company, the proportionate of leaving is much higher compared to, the other 2 and 3 years. But there's an interesting trend here. When people complete 5 years in the company, right, there are more people leaving than staying. So this is could be one of the very interesting insights for the HR to take specific intervention and policy changes, because once the employee completes 5 years, the proportion of people leaving are higher compared to people staying. There could be specific regions, and the HR, because if people have stayed for that long, they will have a lot of experience, and they could be very critical for the organization. If the company thinks, HR thinks, they can actually make a specific policy level changes, right, to retain those employees. So this could be very interesting insight for the HR. But once again beyond 5 years, so you can see 2 to 5 years, the proportion of people leaving gradually increases and reaches peak at the 5 years, but after that it reduces. So once the employee has stayed for more than 6 years, I think we see hardly any employee leaving. There could be very specific small percentage of people leaving. Of course, the number of people who have that many experience are of course very less here, but the proportion is definitely very small. Let's look at one final one, attrition patterns across different departments. So do have different departments, and what are different departments? So if you look at HR_df dot department, and you can see unique values. So there's a department called sales, probably sales and marketing, accounting, HR, technical, support, management, IT, product management. Also marketing is separate, R&D. So the different departments are there. So the pattern of people staying and leaving, is it same across different departments, or some departments people typically tend to stay or tend to leave? You can look at that. So for example, here we will look at cross tab. The reason we can use a cross tab, and of course we can also use a heat map for it, because now the comparison of both the variables, department and left, both are categorical features. So when you have both the categorical features, we can look at a cross tabulation, and we will normalize the data row wise. For example, here each department is captured as rows, and the columns are whether the employee has a not left or left. So in IT, the proportion of people who are leaving are about 22% compared to not leaving, and you can see the R&D, it's quite low. I think the least was management, very few people leaving. This could be very senior people, and R&D as well. Whereas the proportion of people leaving in HR itself is very high, about 30%, and here maybe accounting is the next second highest here. So you can actually explore. It's typically a good idea to kind of explore the data, all the independent variables with respect to the dependent variable, which is categorical here in nature, and understand the different patterns here. This will also help us to do some of the feature engineering, which we'll cover in some of the future sessions. And here there's a participant exercise. You can attempt how last evaluation influences employee's decision to leave. But beyond that, also you can explore other variables like how number of projects influence the decision to leave, or salary, if you're in a high bracket or a medium bracket and low bracket, how the people's behave, whether they stay or leave, the proportionate between these two categories. EDA also help us to kind of understand these variables in deep and what they actually mean, and which actually helps later to build models. So what I'll do now is we'll build a simple classification model. Like we did in the regression, we'll start with a simple model with just one variable, and we'll take satisfaction level as the variable here to predict if an employee is going to leave or not leave an organization. Satisfaction level is a very important variable. So we'll take one variable and build a model and understand what is the mathematical formulation of the model, and then of course we'll expand it to all the variables and build the model and see how the model quality improves. So we'll set an x and y values. The x will be satisfaction level. We're just taking one particular variable, and y is going to be left. And we can see, quickly look at the first two records. And then if you do a scatter plot here between these two, how satisfaction level and left are related, we'll just take a few samples and look at that. And if you look at this plot, this looks very different than the plot that we had done for regression. If you remember, in regression, we tried to predict the shell value of a car with respect to mileage or kilometer driven, right, or age, right? And then we see a continuous scatter of the plot. But here, our x value is satisfaction level, which range from 0.0 to 1.0. But my left value takes the value of 0 or 1. There is no other possible values for the left here. Right. So you can see a pattern here that people who are very satisfied, you can see a cluster of data points here, highly dense compared to this one. That means people who are not leaving, 0 means not leaving, right? So people who are less satisfied, probably the value is less than 0.5 or something. People who are not leaving are very less, but people who are very highly satisfied, you can see a dense of the dots here. So they are mostly not leaving. Same thing, you can see people who are leaving when the left value is 1. You can see the highly satisfied people, again the dots are very less here, but little bit of dense here. So the value of 1 for the variable left is higher in number and frequency when the value is satisfaction value is lesser, probably the less than zero point 0.5 or so, and the value is of left is 0 when the satisfaction level is higher than 0.5. So here, of course, it doesn't make sense to build a model, a linear model like this, right? Instead, we can build a model which might look something like this. So the value of, so in this line, the value of left or y, you can take this as x and this is y. The value of y would be 1 when the x value is low, and the value of y will be 0 when the x value is higher. And of course, this has to be a continuous function. So there will be, of course, certain points of x value when the y value will be between 0 to 1. So this is actually taken as a, there's a function called sigmoid function or logistic function, which can actually be taken for building the model. So we'll look at that. The other thing is y value, in this case left, cannot be any other value with except 0 and 1. But if you take this function, it of course has value is closer to 1 and has value closer to 0, but it also has value in between 0 and 1. So in classification models, typically we don't predict the value of y directly. Rather, we predict the value of the probability of y where the y takes a particular class. For example, what is the probability that y equal to left or 1 as a function of x, in this case is a function of satisfaction level. So unlike regression, which is we can build a model like y equal to a function of x. So the sale value of a car is a function of mileage or age or kilometer driven. In classification models, typically the formulation looks like what is the probability that y equal to 1, that means belongs to the class 1. In this case, class 1 means the people who have left the organization, as a function of x. So in this case, let's say satisfaction level, last evaluation, time spent in the company, and so on and so forth. So that's how it differs, how the regression models are approached and how the classification models are approached. So one of the functions that we can use, like we discussed now, is called logistic regression or sigmoid function, which looks like this. So either it may look like this or it may also look like this based on the coefficient value. And this is actually given by the probability of y, the value of y here with respect to x is 1 divided by 1 plus e to the power minus beta 0 plus beta 1 x. So this particular function, the value lies between always 0 to 1. So if you fit in the x values here, like a satisfaction level or last evaluation, it will actually predict the value of y here. Now, if you build a model like this, for example, if you build a model here, which looks like this. So in this case, if the beta values of beta 1 is a negative, then the model look the other way. the slope is different than the one that is depicted in the picture here, which is likely, most likely here. So let's say we build a model, the sigmoid function. So what is the probability that employee is going to leave, right, as a function of satisfaction level? So as the satisfaction level increases, the probability reduces, so it will be negative coefficient. We will of course understand that once you build the model. But it will predict a value between 0 to 1, because the probability values also varies from 0 to 1. So for some satisfaction level, it will say the probability of leaving is very high, 1 or closer to 1. And for some satisfaction level, it will say the probability of leaving is low, that is closer to 0 or 0. And for some other satisfaction level probably in between, it will have a value between 1 to 0, like for example, let's say 0.8 or 0.7 or 0.4 or 0.3 and so on and so forth. Then how do we predict the actual value of y? Because ultimately when you build a model and deploy it, you have to tell that the employee is going to likely to leave or not likely to leave. For a business, you have to convert this probability value or likelihood score into the ultimate decision making. For example, yes, the employee is likely to leave, so we'll make an intervention, or not likely to leave, probably will not make an intervention. So in this case, what we do is, once we predict the value of probability, we'll take a threshold value, a cutoff value. For example, we'll say 0.5 as a cutoff, and which is typically a default cutoff, and we'll say if the probability value as shown here, so the predicted value of y would be 0. That means in this case, the employee is not likely to leave if the probability value, the predicted probability value is less than 0.5, and 1 if the probability value is more than or equal to 0.5. So this is typically, it's called a threshold value. So in this particular example, we will assume to be 0.5, but we will also look at how to arrive at the appropriate threshold value. Based on certain criteria, we can actually come out with an optimal threshold value. But for the now, we will assume to be 0.5. And the first is, we will build a model to predict the probability of y with respect to x, and then we will take that threshold value of 0.5 to predict the actual value of the predicted value of y, and then we'll compare with the actual value of y to measure how good or bad the model is. So the probability of y is given by the equation here, which is a sigmoid logistic function, and the predicted value class of y is based on the threshold value. It's calculated here. So let's first split the data set into train and test. So scikit-learn model selection, train test split. We'll split x and y with a test size of 0.2. So we have about 14,999 samples are there. And so when 20% is quite largest sample for the test data. And now the shape says that about 11,999 samples are in the train, about 3,000 samples are in the test data. Now we'll build a logistic regression model. So from scikit-learn linear model, logistic regression, and we'll initialize logistic regression model here, and then we'll fit the data x train and y train. So if you see here, the API abstraction is very clean here. It's almost very similar to linear regression, and all that we are doing is, importing the appropriate model or algorithm that we want to use, and then we're initializing that particular model and then fitting our train data to it. But logistic regression is a classification model. And why it is again called a regression model, we will of course come back and explore that little later. We'll skip that for a moment and it will dive deeper in the future session. But this is actually a classification model. Now let's fit the data, and looks like it has fitted a model there. And let's look at the intercept and the coefficients, because in the logistic regression model also there beta 0 plus beta 1. So this is again called the coefficient, the intercept, and this is called the coefficient. So beta 0 is the intercept here, beta 1 is the coefficient here. And if you look at the intercept, it says 0.893, and the coefficient says minus 3.7149. Now you can write the equation like this. The probability that the employee is going to leave, that means the y value equal to 1, would be 1 divided by 1 plus e to the power minus, and then you can write 0.8983 minus 3.71 multiplied by the satisfaction level. So as in when we fit satisfaction level here, it's going to predict the value of the probability here. The negative coefficient here for the beta values here, it indicates that as the satisfaction level increases, the probability reduces. If it had been positive value, if it increases, this will also increase. So this negative coefficient here has a inversely proportional, right, to the predicted value, the probability value here. So what is the meaning of the negative coefficient here? That means the corresponding variable value increases, then the predicted value, the probability value, reduces. So can we observe that now? So let's look at that, the probability of leaving at a different satisfaction scores. We know that the satisfaction scores go from 0.0 to 1.0. So what we can do is we can now observe that. So we'll say, okay, if the satisfaction level increases from 0.0 to 0.05, 0.10, 0.15 up to 0.95 and 1, and then we'll say, okay, in that case, what is the probability when satisfaction score is 0? What is the probability of leaving when the satisfaction level is 0.05, 1.10, and so on and so forth. So we'll calculate the satisfaction level here, given the equation that we got here, and we'll plot against the satisfaction level and probability value, and then observe how it looks like. So here what we do is we'll create a list of satisfaction scores ranging from 0.0 to 1. Okay, you can say ranging, right? So there's a function called NP A range. If you give the minimum value 0.0 and 1.0 and what the step value, it automatically generates those sequence of numbers: 0, 0.05, 0.1, 0.15, and so on and so forth. Now we know that the beta 0 is the intercept value, and beta 1 is the coefficient value. So we'll capture that into these two variables, beta 0 and beta 1. And if we of course print that 0.08983 and minus 3.71. So what we'll do now is we will use this list comprehension, and for x in SL list, that means for every value of 0, 0.05, 0.1, and so on and so forth, we'll apply this particular logistic function, which is 1 1 divided by 1 plus e to the power minus of beta 0 and beta 1 x, right? So this will automatically create that equation that we just wrote, and for every value of x, every value of uh, x in SL list. So for 0 and 0.5, we're going to calculate that and capture that into the probability value here, SL probability. And then we'll capture that into a data frame in two columns, one which stores the satisfaction level, the other one is the probability value. And if you observe this here, this is the satisfaction level and the corresponding probability value, the probability of the employee leaving. So you can see that when the satisfaction score is very low, the probability of leaving is what? Very, very high, 0.71. And as the satisfaction level increases, you can see the probabilities are dropping, they are reducing, diminishing. And when the satisfaction level is very high, like 0.9 or 1.0, this is 0.067, right? And we can draw a plot now, a line plot depicting both of them. On the x will take satisfaction level and the y will take a probability value. And we can see, let's comment this one first and look at the line, and we can see we have gotten that equation here, that model, which looks like the sigmoid function. Okay. So it all depends on the coefficient value. If this particular line will look something like this or look something like this, the slope is increases sharply with steepness or with gradual, all depends on the what is the coefficient value, right? So here coefficient value is very less, that's why you can see this a gradual diminishing of the probability, but you can see there is a S type of curve, Z type of curve here, and as satisfaction level increases, the probability value reduces. And here we can actually take a cutoff value of 0.5. So here that's a 0.5, and you can say people who have so all these people are likely to leave and all these people are not likely to leave. You can actually predict the value of y from here, but whether it's going to be 0.5 or 0.4 or 0.3 is something that we can find out through a different technique, which we'll explore in the future sessions. Now let's take that for the timing, let's assume that it's a 0.5 and then we'll predict it. So in the model, the log reg v1, which is the model that we have built here, logistic regression model, it has a predict function like any other scikit-learn model, and will give the x test. In fact, the log reg v1 in the class, because it's classification model, it has two functions. One is called predict and one is called predict probability. It also has a log probability, which is will not be using. There are two methods here. One is predict and one is predict probability. So if you invoke predict probability, it's going to give the probability value. Then you can apply your own threshold value and then predict the value of y. But if you just simply call predict here, it's going to assume that the threshold value is 0.5 and automatically classify and give you the value of y here. So for the timing, like I told, we will assume it 0.5 and predict the value of y, and we'll capture that into y pred and compare with the actual value of y, which is y test. So this data frame will create two columns, actual and predicted. The actual values are y test and the predicted value is the y pred. And if you take randomly some of the data points, and some 10 samples here. And we can interestingly see here, these are the like employee IDs which are randomly kept in the test data. So we have not kept taken test data in any specific sequence, randomly sampled. And this is the actual value. That means the employee actually left the organization. And here we have predicted that employee is going to leave because this probability value is probably more than 0.5. And this is where we have gotten correct classification, right? We are able to classify this particular sample correctly. This is correct classification. But if you look at the second one, which is the employee actually left, but the model is saying is not likely to leave because the predicted probability is probably less than 0.5. And this is, we got it wrong. We could not classify correctly. So this is called misclassification by the model, right? So same thing, this is also misclassification, this is correct classification. So if you can see, correct classification, misclassifications, correct, misclassification, correct, right? So we got some right and some wrong here in this particular 10 samples that we've taken from the test data. And we have 3000 samples in the test data. So if you remember, when we split the data, we have 11,999 in the train and 3000 samples in the test data. And if we now look at all of the samples, how many we got right and how many we got wrong, what we can do is we can use this particular matrix in scikit-learn called accuracy score, which compares what is the predicted value of y, right? If the predicted value of y is same as the actual value of y or not, right? So how many we got wrong and how many we got right, and then out of 3000 samples and test the score. So this says that 0.768, which is pretty high with just one variable. So almost 77% accuracy we have gotten. So out of 3000 samples, 77% of them we have got correctly classified. The remaining 23% we got wrongly classified. And we got a little higher here with just one variable because satisfaction level is a very, very important variable which tells if the employee is going to stay or leave the organization. It captures a lot of information which also incorporates information about the compensation, about the work-life balance. So many different factors must be embedded into it. That's why getting a very high score here. So that's our attempt to build a simple classification model using logistic regression or sigmoid function, using just one variable, simply taking the variable, building the model, predicting and validating against the test data and checking the first score. Of course, if you take more variable, probably will get a better score, which will of course explore in the next week. But as a participant exercise, I recommend that you build a logistic regression model. Now between average monthly hours and left, like we're done between satisfaction level and left, you take average monthly hours and left. And intuition says that typically if you ask employee to work more and more, the probability of leaving would be higher. So it will actually look like a curve like this rather than this, but you can build and validate that intuition here. And you can generate average monthly hours, like satisfaction score goes from 0.0 to 1.0. And average monthly hours, we can take it from 0 or 50 hours minimum to like 400 hours. Maybe that's a very high number, but you can check the mean and max value of this, okay, and generate different average monthly hours with a step of 10 hours and predict the probability of leaving and not leaving, and then plot it and observe that. You can also measure the accuracy if you take only average monthly hours as one variable to predict the value of y, that is, the employee is going to leave or not going to leave. So that will be a very good exercise. Will basically reinforces your understanding about this particular model, and then we will look at the advanced topics, taking all variables and building a model, and we'll also explore beyond logistic regression what other models are there, and we'll also go very deep into how to measure the accuracy of a classification model beyond the total accuracy here. So thank you and see you in the next session.